Hello, everyone. Welcome and welcome back. And please let me introduce our next speaker of the day. Next up, we have YOUNGJUN CHOI, a senior research scientist at UPS. And his talk today is entitled Data-Driven Drone-Based Urban Last Mile Delivery. Okay, YOUNGJUN, you can join us here on the virtual stage. You can bring up your camera and share your slides. Great.
Thank you.
Sure, I'll turn my camera off and I'll be here if you need anything.
Okay. Today I'm going to talk about data-driven drone-based urban last mile delivery problem. First, I want to introduce my background. I'm a senior research scientist at UPS Advanced Technology Group. I'm working on the last mile delivery solution. And formerly, I was a research engineer at Georgia Tech. And also I was a space system engineer, Agency for Defense Development in South Korea. I got my PhD from Georgia Tech, and also I got my master and bachelor from the Gachon University at South Korea. So today, this talk is not related to any UPS work. All the contents are from my previous work at Georgia Tech. So here is the list of papers I published. All the contents are from those papers. If you are interested, please check those papers. So nowadays, drone delivery system has gained a lot of attention because of potential markets. Because of the many companies like UPS and Google's and Amazon try to invest on a lot of monies to develop the new technologies. There are many different use cases like food delivery, medical supplies, and industrial materials. So today my talk is more like a last mile delivery problem. So to help, to provide your background, first I want to visit the fundamental concept of the delivery system. Let's say we want to order a product. Normally we go to the website and then order the package. After that, the package will be delivered at home, from the store to the collection station, from the collection station to hub. After that, it will go to the delivery station at the home. Normally, the last segment we call the last mile delivery. So depending on the communities and industry areas, the definition is slightly different. So this one is kind of a general definition of the delivery processing. So traditionally, we use our package car or vans to deliver the package from the delivery station to the customer location. So now we want to make a transition using the drone technologies. It means that in order to deliver the package from the delivery station to the home, we want to use the drones because it is very efficient. So now I want to compare two technologies. So in the conventionally, we use the trucks, and now we want to use the VTOL, vertical takeoff landing platform. And in terms of speed, the conventional vehicle is average speed is like 70 miles per hour, and drone, it can be less than 100 miles per hour. Also, if we think about like traffic system, conventional vehicle, it is very highly dependent, like traffic jams and traffic infrastructures. Drone is more like independent. In terms of payload capacity, conventional vehicle can carry more payloads, and drones, it can only carry 55 pounds. This one is more like from the regulation perspective. And then if we think about the endurance, conventional vehicle, normally 8 hours, and drone is very short. Fuel types, conventional vehicle is gas. So now we want to make a transition into the electricity, and drone, normally we use the battery power, which is the electricity. When you operate the drones, we also need to think about recharging strategy. There are two concepts. First, we can recharging the actual battery, and then second concept is we can swap in the batteries. Now I want to introduce like basic delivery concept using the drones. There are many concepts out there. Here I want to introduce 3 representative concepts. So first one is a common drone-based delivery concept. At the delivery station, drone is dispatched and then deliver the package to the customer location. And then second concept is a hybrid concept. It uses package car plus drones. It means that package car is dispatched from the delivery station, and then near the customer location, drone is dispatched from the package car. And then drone will deliver the package to the customers and then coming back to the package car. So this one we call hybrid concept. Second hybrid concept is kind of opposite way. It means that drone is dispatched from the delivery station and then land on the vans, and then van deliver the package to the customer's front door. So these ones are three representative concepts. There are many concepts out there. So in today's talk, I'm gonna focusing on the common drone-based delivery concept. The reason is that this one has more technical challenges, and this one is more common concept. So because of that, I want to focusing on addressing these problems. So now I want to introduce 5 general characteristics of drone-based delivery system. So drone can carry small payload capacity. So based on the current FAA regulation, it can only carry 55 pounds, and then it has a short endurance. Also, it is independent from the conventional road system. So this is a kind of a positive thing. And then we need to follow all the FAA regulation, maximum altitude and maximum speed, maximum weight, vision line of sight. And then also we need to think about the recharging strategies. In here, I'm gonna think about the swapping batteries because it's more efficient compared to the actually charging the batteries. Also the recharging location, I'm thinking the depot only. So now I put the 4 different cities pictures because in the future we want to operate drones in those environments like Manhattan, New York City, and San Francisco, California, and Dubai, United Arab Emirates, and so South Korea. So if we think about those kind of environment, there will be a lot of high-rise buildings. One of the challenging part is that how we can create safe flyable route. So that one is one biggest issues. Also around those cities, there will be a lot of airport that may have no flight zones because we don't want to crash between drone and airplanes. So based on this observation, here is the research question I want to answer. How can we create the analysis framework of drone-based urban package delivery to satisfy those drone characteristics and consider different geospatial constraints? So geospatial constraints can be building obstacles or like regulations like no fly zone because of airport or military base. So to answer those ones, we developed a kind of framework of drone-based urban last mile delivery analysis. So first we select the urban area. So here is an example. We select the San Diego area. And then next step is we're gonna do the urban modeling process. So in here, we're gonna use the airborne LiDAR sensor. So it has a very rich point cloud information. And also we use the FAA database. It has all the no-fly zone informations. And then we combine 2 information together and we apply some machine learning algorithm to simplify the urban models. Because if we looked at this data, it is very huge point cloud data. So using this data and then optimizing drone package route is computationally not efficient. So because of that here, we want to solve the problem through simplifying the urban model. And then once we have that, we're gonna create the flying network. So here we propose 2 level network. One is a low level flying network. It provide safe route. And next one is a high level flying network. this one is for the solving the optimization problem. Once we have that, we're gonna solve the route optimization. So I'm gonna visit all the details later slide. So first, selection of the urban area. Here we select the San Diego environment. And then as you can see here, there is military areas. It has no-fly zones. And it has also airport area. So that one we need to avoid when you create a flyover route. Also downtown area, there will be a lot of high-rise buildings. Also we need to consider when you create a fly network. So next step is the collection of the airborne LiDAR sensor data. So here I want to share the point cloud data. So here is the San Diego downtown, and here is the oceans. And as you can see here, the point cloud information has a lot of noise. At the same time, it has a large point cloud. So one of the challenging part is that how we can simplify this point cloud information so that we can quickly, rapidly analyze drone delivery problem. So in order to do that here, we propose a rapid data-driven grid-based urban modeling methodology. It has 6 steps. First, we collect the airborne LiDAR sensor data. And then based on that one, we're gonna resample the data. This one filtered like noisy informations. At the same time, we eliminate unnecessary data. And the next step, we identify the number of clusters. It will be all the buildings. So here we apply the clustering method, which is one of unsupervised learning method. And then we're gonna apply the principal component analysis to identify the rotation angles of the individual buildings. Once we have that, we'll apply the grid generation technique. This one allows us to adjust fidelity of the buildings, and then we'll get the actual building information. So here I'm gonna skip all the mathematical formulations and machine learning background to save time. So if you are interested, please check out the following paper. So now I'm gonna talk about all the result based on the proposed method. So here is different cities. So we have a San Diego environment and Indianapolis, and another San Diego area and Portland. And here is the image from the Google. And then this one is the LiDAR source. So based on this LiDAR source, we create a high fidelity model and low fidelity model. So low fidelity model, we use the cuboid shape, and high fidelity model, we use the multiple grid. So we have another 4 cities: Salt Lake City, Philadelphia, Pittsburgh, and Louisville. And then here is all the result. If we look the Philadelphia result, as you can see here, high fidelity model capture well about the building shapes, and then low fidelity model efficiently simplify the urban model. So now we have the simplified model. So now I'm gonna talk about how we can define the flying network. So let's say we have 1 depot and 4 different customers. Traditionally, we use the straight lines, which is the Euclidean distance. And then we use this one as a flight network. But the problem is that, as you can see here, some area, there is some collision issues. So traditional method cannot handle those kind of urban settings. So in here, we want to address these issues. So there are multiple ways we can tackle these problems. So here I want to introduce 2 main approaches. So first one is we can use the visibility graph. It connects all the edges based on the building information, which is the object information, only visible part. And then second approach is that we can apply the Voronoi diagram. It creates the edges based on the 2 object locations. So it creates the edges, the center of the 2 objects. So if you look at the complexity, the Voronoi diagram is more efficient. Also visually, we can see that it provides a more safe route. So here is a kind of animation about how to generate the Voronoi diagram. As you can see, based on the object information, it creates a safe route between 2 objects. So we apply that one in our urban environment. So here is the kind of result I want to share. So the cyan, the color, blue color is the Bologna route, which is the safe flyable route. So I create a video here. So here is a video top view. And as you can see, a Bologna diagram successfully create a safe route. As you can see, all the route avoid all the buildings. So the benefit of the proposed framework, we use simplified urban model instead of using reach point cloud information. This is very fast and efficient. So now we have the low level flyable safe fly network. And then we'll have the another network, which is the high level urban flying network based on the customer location. So it has a Euclidean distance. So this one is for solving the optimization problem. And then when we're solving the optimization problem, we use the weight based on the distance from Bologna diagram result. And then here I want to compare the result of Euclidean path and Bologna path. So here is the depot location and here is the customer location. As you can see here, Euclidean path, it violates the no-fly zone. On the other hand, the proposed method, it can provide a safe route. Yeah. So now we have all the flying network. Now I want to talk about how we can solve the optimization problem. Let's say we have the delivery station, which is the depot, and we have 6 different the customer locations, and then each customer has a demand like 5 pounds and 10 pounds. So when you solve the optimization problem, first we need to think about 2 constraints from the traveling salesman problem. First one is each customer should be visited exactly once by a vehicle. Second constraint is each route trip starts and ends at depot. And the next one is that each vehicle has a payload capacity constraint. So in order to put that on as a constraint, we need to use the following constraint. Each vehicle can carry payloads up to its maximum capacity. Next, each customer may have a different time window. They want to get a package. So in here, this customer want to get the package this time period. So in order to consider this constraint, we need to consider the following statement. The first one is the vehicles can deliver payload to customers within time window only. Second one is if vehicles arrive at the delivery location earlier than the time window, they should wait until satisfying time window. Next, we need to think about the reusability of the UAVs. So in order to do that, we need to consider the following constraint. Reloading payloads and exchanging batteries are conducted at depot only. So today I'm gonna skip all the mathematical details. So if you are interested in cost function, how to formulate the constraint, please check out the following paper. So here I'm gonna talk about numerical simulation. We select an area, which is the San Diego area as a test case. Here is the point cloud information. Simulation condition is we define the single depot and 20 delivery locations. And then demands and time window, we use the discrete uniform distribution. Operating altitude, 20 feet AGL above ground level. Service time is 10 minutes. Time to reloading packages, swapping batteries, 20 minutes. And total operating period, 8 hours. Vehicle speed, 50 miles per hour. Vehicle payload capacity, 10 pounds. Vehicle maximum endurance, 45 minutes. So we have different cases. Here I want to address one examples. So here we formulate the 4 different optimization framework. One is a single trip, single package model. Drone can deliver only single package. We can reuse the drones. Second one is a single trip and multi-package model. Drone can deliver multiple packages, but we cannot reuse the drones. Next one is a multi-trip and single package model. Drone can deliver a single package and we can use the drones. And next one is multi-trip and multi-package model. Drone can deliver the multiple package and we can reuse the drones. Now I'm going to talk about the result. So here there is 4 different methods: single trip and single package model, single trip multi-package model, multi-trip single package model, multi-trip and multi-package model. Here is the object function, which is the cost. We didn't have the financial model, so we assume acquisition cost and operating cost. Here is the result. And as you can see here, the multi-trip model is more efficient because we can reuse the drones. And then if you look at the number of UAVs, the multi-trip model can use only required 2 UAVs instead of more UAVs. So this is a more efficient method. And then if we think about like computational efficiency, the single packaging model is better because in terms of the mathematical perspective, it is more like harder constraints. Because of that, the optimizer can solve very quickly. So for the result, I want to share one visualization outcome from the multi-trip and multi-package model. And here is the result. So and this is top view, and red dot is the gas stations we collected. And then it required 2 UAVs. Because of that, there are 2 colors. As you can see here, all the result successfully create all the delivery route without any collision issues. So this one is very extremely computationally efficient because we use simplified urban models and then automatically generate the route from the Voronoi diagram. So here is my conclusion. So I introduced the modeling and simulation framework for drone-based urban last mile delivery. So proposed framework uses the LiDAR data and FAA regulation database to consider the geospatial constraints, also introduce novel flight network generation and optimization technique. I believe that this framework is extremely useful to perform the rapid operational analysis depending on the different geolocations. So I appreciate YOUNGJUN and Nicole to support my research. Also, I really thank UPS Advanced Technology Group. Thank you so much.
Okay, that was great. Thank you so much. If you could please, there you go, turn off your camera. Well, thank you so much. I hope you all enjoyed. That was a really great talk. Please give another virtual round of applause for YOUNGJUN and stay with us to check out your next session or maybe hit up a one-on-one networking session. Have a great time.